Using a horizontal tail isn't the only way to trim or make an aircraft that is trim and stable in pitch. Another option is what's called a wing canard design, and this is where you have a canard, the smaller wing actually in front of the bigger wing. So let's draw a simplified analysis of this, and actually I'm going to draw these. We're going to draw our fuselage reference line here, and we're going to draw the canard here at an angle of attack, and the main wing at an angle of attack to that fuselage reference line. Okay, and again, we're going to assume that thrust is aligned with that fuselage reference line, and that V infinity is also aligned, and that we're at an angle of gamma to the horizon, and we'll put our center of gravity up here in the front and measure all distances aft of that. So we'll have L sub h. We're still going to call this the horizontal. So we'll use a subscript h, and then this is the length to the main wing. So the weight acts through the center of gravity, and then the main wing and horizontal can be mounted. So this would be alpha naught h, and this angle here would be alpha naught wing. So those would be the mounting angles. And then we can draw the lift on the main wing, which is perpendicular to the direction of flight. The drag is aligned with the direction of flight, and then the pitching moment from the wing. So these are lift, drag, and pitching moment, and then we'd have the lift, drag, and pitching moment on the horizontal. Now, just like if we had downwash behind the main wing, we actually get upwash in front of the main wing. So we actually have some increase in angle of attack here. So we'd have some velocity in the y direction, say, but we'll have some increase in angle of attack here that we'll call epsilon upwash, that will be acting on that horizontal. And so the lift here is actually rotated a little bit forward. Lift on the horizontal and drag on the horizontal. Those will be rotated according to that upwash. And then, of course, we can have a pitching moment from the horizontal. Okay, so this is our free body diagram, and we can go through the same type of analysis that we did last time, and I'm going to just kind of cut to the chase on a few things. So for example, if we sum forces in the direction of lift on the entire aircraft, then we get the coefficient of, and non-dimensionalize it, we get the coefficient of lift on the main wing plus SH over SW times the coefficient of lift on the horizontal is equal to the coefficient of weight, or weight over 1/2 rho V infinity squared, times the wing area, times cosine gamma. Cosine, or gamma, is our climb angle again. And then so this is one of our trim equations. And then we can also write the forces in the direction of drag and thrust, but all that's going to tell us really is the throttle setting required to trim. And so let's now go to the pitching moment. In order for this to be trim, the pitching moment about the center of gravity has to be equal to 0, which is the pitching moment of the main wing plus SH over SW times C bar H over C bar wing times the pitching moment on the horizontal minus LW over C bar wing lift coefficient on the main wing minus SH LH over SW C bar wing times the lift coefficient on the horizontal has to be equal to 0. So that's our pitching moment equation. And then finally, we can talk about stability. And that is that Cm alpha has to be less than 0. So if we take the derivative of our pitching moment equation, and notice that, so this pitching moment of the main wing and of the horizontal, those are about the aerodynamic centers of the main wing and horizontal. And so when we take the derivative with respect to alpha, those are 0, or the derivative is 0. So we're left with minus LW over C bar wing times CL wing alpha, minus SH LH over SW C bar wing, CL horizontal alpha, and that has to be less than 0 to be stable. Okay, now the lift coefficient, so these are our main equations. These three equations ensure trim and stability if we're satisfying all of those. And let's just dig into the lift coefficient on the main wing here really quickly. Of course, that can be written as CL wing alpha times alpha plus alpha naught wing, that's the mounting angle, minus alpha lift naught wing, which is the zero lift angle of attack. And then the coefficient of lift on the horizontal would be CLH alpha, alpha plus alpha naught horizontal, the mounting angle, minus alpha lift naught horizontal, the zero lift angle of attack. And now we're going to do plus epsilon u. Epsilon u is the upwash, and then plus epsilon e times delta e. Of course, we can have an elevator deflection here that we call delta e. Okay, now epsilon upwash here, we can treat the same as downwash. It's going to be epsilon upwash naught plus epsilon upwash with respect to alpha times alpha. So this is, again, just a linear relationship in our upwash angle with respect to angle of attack. Okay, one thing that I've assumed in this development is that eta, I'll just put it down here, eta h equals 1.0. And the reason that that's a pretty good assumption here is because the main wing, or excuse me, the horizontal is out in front of the main wing. Remember, eta h is our efficiency, our tail efficiency, that has to do with the ratio of the dynamic pressures that the horizontal is seeing compared to the dynamic pressure on the main wing. And because the horizontal is out in front of the main wing, in this case, it's basically seeing the free stream velocity. And so, so this is not a bad assumption here for this. So I've actually just dropped that out. That would have appeared in a few places in these equations up here. Okay, so now when Phillips develops this in his book, he actually rearranges these equations to prove a few things. And I'm not going to walk through that whole thing, but there are some really important takeaways that I'm going to point out here. So first of all, from the pitching moment equation, let's just walk through the signs here on the pitching moment equation. So the pitching moment on the main wing is going to most of the time be negative. That's because we usually have positive camber on the main wing. The pitching moment on the horizontal, we're going to assume that that's either negative or 0. So it has positive camber or 0 camber. And then the lift coefficient on the main wing is positive, and the distance to the main wing, L sub W, is going to be positive as well, because that main wing is going to sit behind the center of gravity, and so this entire term here is going to be negative. So in order for us to trim this aircraft, this last term here has to be positive, and by the way that he develops it in the book, you can prove that L sub h has to be negative. Okay, so that's got to be a negative right there, and so that's one of the things that's a takeaway here, is that L sub h has to be less than 0, meaning that the horizontal or the canard, excuse me, has to sit in front of the center of gravity. Remember, L sub h is the distance between the CG and the horizontal, and you can prove here by manipulating, actually, you have to use both of these equations up here, but you manipulate those to prove that L sub h has to be less than 0, okay? So that gives us a negative here, And so actually you can see from that, if that's true, that so we've got a negative there, so that will make this term positive as long as the lift coefficient on the horizontal is positive. So CLH has to be greater than 0. Okay, so whereas with the traditional aircraft where we have a main wing and then a horizontal stabilizer behind, that the lift on the horizontal could be positive or negative at different points in the flight to trim, and it would still be stable. But in a wing canard design, the lift on the canard must always be greater than 0. You always have to be carrying positive lift. Now that has a few implications and repercussions that we'll talk about here in just a minute. Another thing that we see then is if we look here at the pitch stability derivative, so if L sub W is positive, then that means, and of course the lift slope is positive, that means that this first term is going to be negative. And if L sub H is negative, and of course the lift slope is positive, then this term is going to be positive because you have a negative out front. So one thing that we see here is that the horizontal stabilizer, or the canard, has a destabilizing effect. This term here will always be positive, and so it hurts your pitch stability. And what we find here is that the stability of this aircraft actually comes from the main wing, not the horizontal. So it's kind of incorrect to call this a horizontal stabilizer. The canard is actually a destabilizing aerodynamic surface. It sits in front of the center of gravity, and we get our stability actually from the main wing, not from the horizontal. So one thing here is that we're going to find that L sub W has to be greater than 0 in order to stabilize the aircraft, and that simply means, and so our stability will come from the main wing, not the canard. Okay, another thing that we can prove is that the lift coefficient on the horizontal actually has to be greater than the lift coefficient on the main wing. And again, I'm not going to walk through and prove that, but you can manipulate these equations to demonstrate that. And so this has some actually really interesting implications. One of those is that because the lift coefficient on the horizontal has to be greater than that on the main wing, we want our horizontal to actually be very efficient. And so usually you'll see very high aspect ratio canards. So usually that means you have a high aspect ratio horizontal because you're trying to get that lift coefficient up in an efficient manner. The next thing is that because of this, if you have flaps on the main wing to increase your lift there during takeoff and landing, you also have to have flaps on the horizontal because your lift coefficient on that canard has to be greater than the lift coefficient on the main wing in order to be trim and stable. And so that means you're going to probably have flaps on the canard. And finally, if we look at stall, this is actually a very good thing for stall because as you increase your angle of attack, so if we increase the angle of attack, then remember this canard sits actually in front of the center of gravity here. Then because it has a higher lift coefficient, then the canard will usually stall before the main wing. That's actually a really nice thing because at high angles of attack then, if the canard stalls, then it will pitch the nose down to an angle of attack that is below stall and makes a nice stall recovery. And so this is one of the benefits of a canard design is that it has good stall handling qualities usually. Now, or good stall characteristics. Now you can still stall the main wing on a canard design if you do a really fast maneuver where you whip the nose up. That's called a whip stall. But for gentle maneuvers, then it's very difficult to actually stall the main wing on a canard design because the canard will stall first and pitch your nose back down. So one last thing that maybe I should point out with the with the flaps, the mention of flaps, is that it requires quite a bit of lift on the canard to rotate the nose during takeoff. And so these are actually, a canard design is usually not a very good design for short takeoff and landing type aircraft. And so you usually don't see them for those types of missions. Now, one thing to note is actually the very first powered aircraft developed by the Wright brothers, the Wright Flyer, was actually a canard design. They had a horizontal stabilizer, or I shouldn't call it stabilizer, the horizontal in front, and in this canard design, and then the main wing in the back. And shortly after that, they went away from that, mostly, we think, to avoid patent issues. Subsequent designers didn't want to infringe on the patent of the Wrights, and so by putting the tail in the back, they were able to get around that. And actually, most aircraft today have a tail in the back, not because of that, but because we've learned these types of things about benefits of having your horizontal in the front in a canard position or in the back. And so today we mostly see aircraft with them in the back, but there are some with that still have a canard design, and I'm going to show you this one right here. This is called the Beechcraft Starship, developed by Burt Rutan's team. And let's just, you can just Google these images, but I'm just going to pull up this image here. This is kind of interesting because you can see the flaps on the main wing. You can also see flaps on the canard. So remember, we talked about if you're going to add flaps to your main wing to increase the lift at low speeds for takeoff and landing, then you also have to put those flaps on the canard, because the lift coefficient on the canard has to be higher. Now, one of the drawbacks of a canard design you can see from this particular view here is that often a canard can get in the way of the view of the pilot. So whereas on traditional aircraft with the horizontal behind the main wing, most of the time the pilot is sitting out. The center of gravity can be very near the aerodynamic center of the main wing, and so the pilot can be sitting forward of that and have a really nice view unobstructed. But with the canard design, the center of gravity is behind the canard, has to be behind the canard. The canard has to be out front, and so that can get in the way of a pilot's view. So this is just maybe one of the drawbacks of the canard design. So hopefully that overview is helpful. Again, we can use the same type of analysis as what we did before. And what we've developed here is simply these three equations, two trim equations, one stability equation, that have to all be satisfied. And of course, we could plug in these equations for the lift on the main wing and the horizontal. We could plug those into these equations and solve them for the operating angle of attack and elevator deflection required to trim. Or we could find the neutral point, the static margin, all the same types of things that we did in our previous analysis with the using a horizontal stabilizer. These equations are just slightly different, and of course we're using upwash on that horizontal instead of downwash because it sits out in front of the main wing. One last thing to mention about downwash is that the canard actually does produce downwash on the horizontal. You can imagine that because the lift coefficient has to be significant out here. In fact, it has to be greater on the canard than on the main wing. That this is also producing downwash. Usually, it has a lower wingspan than the main wing, and so you're really only producing downwash on a portion of the main wing. We can see that if we draw a top-down view. So here's our canard. And then here's our main wing, so we'd be getting downwash here, over a region of the main wing. This type of thing is very difficult to analyze analytically, and so we don't have a good model or a real good simple model for predicting the effects of downwash on the main wing from the canard. But the simplified model that we developed in the previous lectures for downwash from the main wing, remember we put a vortex system here across the main wing and assumed that it had some vorticity that looks like that. And then in the previous video we had a horizontal sitting here, but now we've got our canard out front. But the math of that whole system still works out. It doesn't matter where your horizontal is sitting. And so the equations that we developed are still accurate. It's just that you're going to have your canard out in front of the main wing instead of behind. And so the variable that we used in this direction was x. You're just going to have a negative x value when you plug it into those equations, and it will produce it will estimate the upwash in that region instead of the downwash.